Swayam Prabha. Digital India. Educated India.
Hello everyone, in the previous class we learnt about some of the basics of the regression analysis. Then I introduced you to some of the empirical criteria which were applicable in case of rocks and rock masses. Today we will learn about the most commonly adopted empirical failure criterion in case of rocks and rock masses, which is known as Hoek and Brown criterion. This was given in 1980 by these two authors, Hoek and Brown. The failure within the soil mass, it occurs in shear, we all know this, and therefore it is common to present the failure criterion in terms of shear and the normal stresses on the failure plane. But in case of rock mechanics, it is the common practice to represent the failure criterion in terms of principal stresses, which are sigma 1 and sigma 3. It is the convention to represent the major principal stress by sigma 1 and minor principal stress by sigma 3. So, therefore, for most of the failure criterion in case of rock mechanics, it is a functional relationship between sigma 1 and sigma 3. This Hoek and Brown criterion is valid for intact rock as well as the jointed rocks, and that is one of the reason that it is quite widely used in rock mechanics. So, for the intact rock, we have seen that there were deficiencies of Moore Coulomb criterion when this was applied in case of the rocks. What were these deficiencies? If you recall our discussion with respect to this Moore Coulomb criterion, we discussed that in case of the rock mass where the discontinuities are also present, it is not really possible to get the parameters of Moore Coulomb failure criterion in terms of effective stresses. And therefore, we just left there with a big question that how to determine these parameters. So, in view of those deficiencies, this criterion which was given by Hoek and Brown, it takes care of some of those deficiencies. So, let us see first that how the Hoek and Brown criterion is applicable in case of the intact rock, and then we will see that how it has been extended to the rock mass, and then we will see how the parameters of Hoek and Brown criterion can be used to determine the parameters of Moore Coulomb failure criterion. So, this Hoek and Brown criterion in terms of effective major and minor principal stresses on an intact rock at the failure, which is sigma 1 f prime and sigma 3 f prime respectively, it can be related by this expression, which is sigma 1 f prime is equal to sigma 3 f prime plus sigma c I into m I sigma 3 f prime divided by sigma c I plus s to the power 0.5. So, this is the equation for Hoek and Brown criterion, where the sigma Ci is the UCS of the intact rock material, M and S. These are the constants that depend on the properties of rock and also on the extent to which it had been broken before being subjected to failure stresses, which are sigma 1f and sigma 3f. Now, in case of this equation, if we substitute this sigma 3f equal to 0, that means confining pressure is equal to 0. So, what we are going to get as an axial stress, as it will be the UCS of the intact rock. That is what that we are going to get. So, just substitute these values in the expression, and what you are going to get is, see, I just do it, sigma Ci, that is equal to, first term will become equal to 0 plus sigma Ci, and then inside the bracket first term will become equal to 0 plus S to the power 0.25. And what this equation gives me is that for this equation to be satisfied, this S should be equal to 1. And therefore, we can conclude that for intact rocks, this parameter of Hoek and Brown criterion, which is S, that will be equal to 1. Now, if we just substitute this S is equal to 1 in, now if we just substitute this S is equal to 1 in the Hoek and Brown criterion equation, so that equation can be written as sigma 1f prime minus sigma 3f prime whole square. This is equal to m sigma Ci sigma 3f prime plus sigma Ci square. This is for the intact rock with S is equal to 1. Now, we have seen that how the equation for the intact rock looks like. So, if we plot the triaxial data as sigma 1f minus sigma 3f whole square versus sigma 3f, we can plot a straight line between these two, and from there we can obtain Mi and sigma Ci. So, the parameters were S, M and sigma Ci. So, this is the way we can find out Mi and sigma Ci, and you have seen that S is going to be equal to 1 in case of the intact rock. Now, if it is not possible to get this Mi from this triaxial test data, then we can find out from this table, that is depending upon the various rock types. Here the value of M has been given. We have discussed this table earlier as well. Say in case of the marble it is 10.6 and in case of norite it is 23.2. As the quality of the rock gets better, it corresponds to the larger value of M. You can see here that granite has large value of M as 27.9. So, basically this Mi is a petrographic constant which is analogous to the friction angle, and the strength increases with increasing values of Mi. For the intact rock, the variation of sigma 1f against sigma 3f as per Hoek and Brown criterion and Moore-Coulomb criterion has been shown here. So, the first plot, which is A, this corresponds to Hoek and Brown criterion and B corresponds to Moore-Coulomb criterion. You have seen in case of the Moore-Coulomb criterion, this relationship was a straight line where the intercept on sigma 1 axis was giving us the idea about the UCS, and the intercept on x axis is giving us the idea about the tensile strength. But in case of the Hoek and Brown criterion, this is how the variation is going to be. So, in this case, it is not a straight line, as you all can see. So, this is kind of a parabolic variation. Where this point corresponds to the uniaxial compression, because here sigma 3 is equal to 0. So, whatever is the value of sigma 1, that is going to give you the UCS, which is sigma c, and this point corresponds to the results for the uniaxial tension. So, this sigma t is going to give us the tensile strength under uniaxial tension. So, if you compare these two criterion, this is straight line, it is the parabolic variation. Why it is more commonly adopted in case of rocks? Because most of the time when you conduct the test on the rock, when you conduct the triaxial test on the rock, this is the kind of variation that you will get and not the straight line. So, as I mentioned, its variation of sigma 1f against sigma 3f as per Hoek and Brown criterion is the parabolic failure envelope. In case of the Moore-Coulomb criterion, it was a straight line, and the intercept on sigma 1 axis and the sigma 3 axis gave us respectively UCS of the intact rock and uniaxial tensile strength of the intact rock. Now, we just substitute this sigma 3f is equal to sigma ti with its appropriate sign. So, we have substituting sigma 3f prime is equal to minus sigma ti, and when this is going to be there, when you will have sigma 1f prime which is equal to 0. In Hoek and Brown criterion equation. So, what we are going to get is, take a look, 0 equal to minus sigma ti plus sigma ci into mi minus sigma ti divided by sigma ci plus s to the power 0.5, and this can also be written as sigma ti divided by sigma ci whole square is going to be equal to minus mi sigma ti upon sigma ci plus s. Or if we try to get this ratio, we can write it as minus mi plus minus square root of mi square plus 4s divided by 2. So, from here we can see that this ratio, which is the ratio of compressive to tensile strength of an intact rock, this depends upon only mi, as s is equal to 1 for intact rock. Right. So, you see that for the intact rock, this quantity is going to be equal to 1, and therefore, this ratio will be only the function of m. Now, this ratio sigma Ci upon sigma Ti increases with increase in mi. And if we take a range of mi, so from 5 to 35, so for the range of mi from 5 to 35, this sigma Ci upon sigma Ti lies within 5 to 35. You can just check it with the help of the calculator. Just substitute the value of m between any value between 5 and 35, and you will get that this will be approximately equal to the value of mi which you have taken. So, we can say that approximately this sigma Ci upon sigma Ti is equal to mi. That can be seen. Now, this was all about the intact rock. I mentioned to you that this criterion can be extended or applicable in case of the rock mass. Let us see how this is done. So, over a period of many years, this Hoek and Brown failure criterion has been evolved as more generalized Hoek and Brown failure criterion and is also applicable in case of the rock mass along with the intact rocks. So, for the jointed rock mass, this is how the expression is written for the Hoek and Brown failure criterion, which is sigma 1f prime is equal to sigma 3f prime plus sigma Ci sigma 3f prime divided by sigma Ci plus s to the power a. Now, here this parameter is nothing but the m parameter which we had in case of the intact rock as well for the rock mass. And because it is for rock mass, therefore, this subscript has been added here, and this can be derived from mi, which is for intact rock. How? See, is written as mi exponential of GSI minus 100 divided by 28 minus 14d. You remember this GSI we discussed when we were discussing the chapter on the classification of the rock mass. This is what is your geological strength index, and this D factor is a factor which accounts for the disturbance in the rock mass. So, this D is the factor accounts for the disturbance in rock mass due to blasting and the stress relief. I will tell you little later that how this parameter is determined. For the time being, just keep in mind that this D varies in the range of 0 to 1. 0 stands for the undisturbed rock mass, while this 1 is for highly disturbed rock mass. So, basically this undisturbed rock mass means there is no disturbance because of this blasting, or there is no stress relief because of the excavation phenomena. So, this is like kind of undisturbed situation. But then in this case you have seen that we still use sigma Ci for intact rock even for the rock mass H. Hoek and Brown criterion. So, although it is for the rock mass, but the term sigma Ci which is there for the intact rock comes into picture. Now, this constant mm which is for the rock mass, it can take the positive value in the range of 0.001 to 25. Highly disturbed poor quality rock masses, they will fall towards the lower range, and hard and almost intact rock will be at the upper end. Intuitively we can say that because of the fact that rock mass, they are weaker than the intact rock because of the presence of the discontinuity, intuitively mm will be less than mi. Typically this mi is going to be in the range of 2 to 35. This difference between parameter m for the rock mass and for the intact rock, which is mm minus mi, is larger with the poorer quality rock mass which has low value of GSI, that is geological strength index. Due to the presence of the discontinuities, UCS of the rock mass, which is represented by sigma Cm, will be less than the UCS of the intact rock, which is represented by sigma Ci. These constant S and A for the rock mass can typically be determined by these expressions, which are given as S is equal to exponential of GSI minus 100 divided by 9 minus 3d. D is again the same disturbance factor, and A is equal to half plus 1 by 6 e to the power minus GSI upon 15 minus e to the power minus 20 upon 3. So, this is how the constants for the rock mass, which are S and A, these can be determined, and we have already seen how the parameter m for the rock mass can be determined. So, this generally this S for the rock mass, it varies in the range of 0 to 1, and as explained earlier, mostly in the lower end of the range with 0 corresponds to the poor quality rock and 1 for the intact rock. The petrographic constant, which is S only, is very much similar to the cohesion in Moore-Coulomb failure criterion. The constant A is 0.5 for the good quality rock or the intact rock, and it takes a value of 0.65 for poor quality of rock. As mentioned, D is a factor to account for the disturbance within the rock mass due to blasting, stress relief and other such phenomena, and it varies in the range of 0 to 1, 0 for the undisturbed rock mass and 1 for the highly disturbed rock mass. In case of the Hoek and Brown criterion, the assumption with its development was that the intact rock and the rock mass, they are going to behave in an isotropic manner. So, this criterion has been found to work well in case of the intact rock specimen and the closely spaced heavily jointed rock masses where you can assume the isotropy. But where you have the situations that the structure that you want to analyze and the block sizes which are there in the rock mass, if they are of the same order in size, or if you have the situations with weak discontinuities, then in that case this criterion should not be applied. So, once again please keep in mind, as long as the material or the rock mass or the intact rock can be assumed as an isotropic material, Hoek and Brown criteria works well in such cases, but in these cases it is not applied. Therefore, for the rock mass, the criteria as sigma 1 f prime is equal to sigma 3 f prime plus sigma Ci, and we have sigma 3 f prime divided by sigma Ci plus S to the power A. Now, you just substitute sigma 3 prime equal to 0. So, what we are going to get is sigma 1 f prime will be sigma Cm, which is UCS of the rock mass. So, just substitute it here and see what you get. So, this is what is going to be sigma Cm. This term will become equal to 0 and this term will also become equal to 0. So, ultimately you are going to get sigma Ci S to the power A, and we know this sigma Ci is UCS of the intact rock. Now, how to get the sigma Cm from the other way? So, Marinos and Hoek in 2001 gave empirical relationship for the UCS of rock mass, and that is given as sigma Cm is equal to sigma Ci multiplied by 0.0034 mi to the power 0.8, this whole thing multiplied by 1.029 plus 0.025 e to the power minus 0.1 mi, and this whole thing to the power GSI. So, for sigma Cm upon sigma Ci tending to 1, what does that mean? That the UCS of the intact rock and UCS of the rock mass, they are equal to each other. This would correspond to the situation when this GSI increases to 100. So, you just see that, substitute this here as 100 and then you will be getting that this ratio will be approximately equal to 1, or it will be tending to 1. Then, assuming A is equal to 0.5, let us try to find out the equation for the ratio of tensile to compressive strength of the rock mass. So, first let us try to see what was that equation for the intact rock. So, this was sigma Ti divided by sigma Ci was equal to minus square root of mi square plus 4s minus mi divided by 2. This was for the intact rock, and obviously this s would be equal to 1 for the intact rock. But right now I am not substituting it equal to 1 because I want to extend this expression in case of the rock mass. So, that is how what we are going to get as a uniaxial tensile strength of the rock mass, that I would represent as sigma Tm, that would be minus sigma Ci, okay, and that is going to be square root of mm square plus 4s minus mm divided by 2. Okay. So, just take a note of it here that this negative sign would be here. So, this is how that we are going to get the uniaxial tensile strength of the rock mass. For the brittle materials, the uniaxial tensile strength is going to be equal to the biaxial tensile strength, and therefore, just substitute sigma 3f prime equal to sigma 1f prime is equal to sigma Tm in this equation, which was sigma 1f prime equal to sigma 3f prime plus sigma Ci into sigma 3f prime upon sigma Ci plus s to the power a. Just substitute it in this, what we get is sigma Tm is equal to sigma Tm, because sigma 3f, sigma 1f and sigma Tm, they are equal to each other, plus sigma Ci and mm sigma Tm divided by sigma Ci plus s to the power a. This will get cancelled out. So, what you are going to get from here is mm sigma Tm to the mm sigma Tm upon sigma Ci plus s would be equal to 0, and therefore we will get sigma Tm equal to minus s sigma Ci upon mm. So, this is how in such situation for brittle materials only, this is for brittle materials, you can get the tensile strength of the rock mass in such manner. So, today we discussed about the Hoek and Brown criteria, which is one of the empirical criterion most commonly adopted in case of rock and rock masses. We saw the different aspects related to this criterion. So, in the next class we will learn that how the parameters of Hoek and Brown criterion can be useful in order to get the more Coulomb failure criterion parameters under effective stress condition. Thank you very much.